Thank you. As everybody, thanks for the nice organization of the conference. I have been working on this program for quite some years, and here we came to some conclusions, so that I would like to talk about for the lattice, exact lattice supersymmetry. The formulation is general enough so that it can be applied to the non-SUJI case as well. The work has been done in collaboration with Alessandro Dada and Jun Saito. Unfortunately, Alessandro was supposed to come here, but because of the health condition, he couldn't come. So our attitude for the lattice SUJI is that to keep exact supersymmetry. If we keep exact SUJI, and what formulation we are forced to reach, that is a question. And then in addition to the motivation which Simon and also Wagner explained, our interest is like algebraic and geometrical understanding of supersymmetry, hopefully to understand some hint for the SUJI breaking mechanism. I think there are three schools here in this audience that about the supersymmetry, how to keep the supersymmetry. The one school is conventional approach, so that you put the fermion and boson on the lattice, and then somehow the supersymmetry is broken, but in the continuum limit it would be recovered, so hoping in this way. The second one is Simon stressed that part of the supersymmetry, of the extended supersymmetry, which is nilpotent part of the SUJI, is kept exactly. However, the other supersymmetry are supposed to be hoping to recover in the continuum limit. Then the third approach is our formulation, our attitude to keep all the supersymmetry exact. Is that really possible or not? And that's a long story. And we have proposed two formulations for this. And one is called link approach. The other is a super double approach, which I'm going to explain here. And this is the extension of this formulation. So what is important is that we consider the SUJI algebra of the formulation, which includes the derivative. Let's consider the simplest possible SUJI algebra, which is supercharged square is Hamiltonian. Hamiltonian is the derivative operator. And on the lattice, derivative operator is replaced to the difference operator. Here I introduce the symmetric difference operator. Now, this formulation is twisted supersymmetry, I would say. Then there are two major difficulties. The first one is, as already mentioned, that the difference operator does not satisfy Leibniz rule, while the supercharge operation satisfies Leibniz rule. Therefore, at the tree level already, the supersymmetry is broken. Surface term cancellation and other things, quantum effect, have also the difficulty because of this reason. Another issue is common problem of the fermions on the lattice. Species double comes in, and the problem is that the species double is a physical particle, so that from the understanding of the helicity is a physical particle, so we have to increase the number of the fermions so that the boson number and the fermion number is unbalanced. So we have to solve this problem also. Do we try to challenge to solve both of these problems at the same time? That's the only way to proceed, probably. Now, one may wonder, lattice QCD chiral fermion solution can be used for this second part. But if you use that form in this way, then the fermion and boson treatment would be changed. Fermion propagator does not have a simple relation with the boson propagator because it is treated differently. Therefore, the vacuum energy cannot be perturbatively exactly cancelled. So from our exact Tsuji point of view, this is not the way to use. So how do we attack to this question? Let's first consider the product of the two fields in the momentum space. And if you go back to the inverse Fourier transform, where x is a lattice coordinate n times lattice constant, and then inverse Fourier transform it, integrate is x out, then we get this expression. This is a well-known convolution formula for the two products. Now let's consider the following situation. P1, P2 are lattice momentum. Now this momentum conservation of the delta function is now replaced into this way, where delta P is a function of the lattice momentum. We will specify the functional form later. Since this part is replaced from here to there, and then the original integration variable is same, therefore the product should be somehow changed from this standard product to so-called, we say, star product. The product itself can be explicitly calculated by going back from momentum representation to the coordinate representation. It's just this expression here, where the delta function is now parameterized in this way. Then if you look at J function, which have three J comes in, and J has this explicit form where delta P, if delta P is momentum itself, then it's a delta function. But since it's not delta, it's a function of P now, so that this is a normally complicated function. But what it turns out is that the product from the standard product turns into the non-local product. The non-locality can be discussed later. So in the coordinate space, N1 and N2 should be summed up all over to define N coordinate product. So in this way, this is a non-local product. K is giving the kernel for that. However, this gives a solution for the first problem. Namely, let's use delta P, which is a momentum representation of the symmetric difference operator. Let's use delta P as sine P over A, replacing this convolution formula into the momentum representation of the difference operator. Now, if you operate P hat for the product of the momentum representation of this star product, P hat is equal to P1 hat plus P2 hat. Therefore, distributed rho in the momentum space is realized. Since P hat itself is in the coordinate space, difference operator itself, therefore, difference operator itself should satisfy Leibniz rule on the star product. But that product is non-local. So this is the way how we solve this first question, that on the star product, difference operator, symmetric difference operator exactly satisfies the Leibniz rule. Now, this identification, which we just identify as a continuum momentum, is now identified as this quantity. It has a natural reason that to identify this way. Let's look at the lattice momentum, which usually identified from this difference operator momentum representation. It's an angular variable. It has a topology of S1, while continuum momentum, which I write P hat, is R1, R. Therefore, topologically, this P and P hat is different. we usually identify conventionally continuum momentum Behat is equal to the lattice momentum. But topologically, these are the two different quantity. This is the origin of the species doublets. So therefore, we think this one has a R topology is natural to be identified as the conserved momentum. That's one logic which we just put on. However, this delta P sin AP, is that unique or not? The first question is, if we require the Hermiticity means that the momentum representation of this difference operator should be real. We cannot use forward-backward difference operator because it's imaginary. Hermiticity is not satisfied. Usually, of course, forward and backward difference operator is used at the same time, but effectively it is same as this symmetric difference operator. Now, the point here is that the symmetric difference operator is not the translation generator of the lattice constant A. It's a two-way step generator. But now let's look at it in this way. Suppose this two-step lattice constant generator is a translation generator. We consider that the physical states are translationally invariant. So what are the sort of the states which are invariant under the two-step translation generator? Constant is, of course, translational invariance with respect to the two-way step. But there is another one which corresponds to -1 to the n, where n is integer. This is invariant under the two-way step of the translation. Actually, this is violating strongly in the coordinate space, which actually corresponds to the species doublet state in the momentum space. So somehow corresponding to the translation generator, there are 2 degrees of freedom in each direction. So we want to have the following situation. Introduce half-lattice structure and lattice shift A as a translation. How can we do that? We can just identify delta symmetric difference operator divided by 2. Namely, A times 1, A half times integer is now the lattice coordinate. So we introduce half-lattice structure. Then if we introduce, these are the lattice space in the realistic space-time, and these are the sort of the newly introduced degrees of freedom. What is a half-lattice shift then? From this geometrical relation, the square of the supercharge is single-step difference operator. Then Q can be identified as a half-lattice difference half-lattice translation generator. Since these are the original lattice, these are the newly introduced degrees of freedom, and it is not necessarily the real space-time. This picture has a very good consistency with the link approach picture. So we introduce this way, the half-lattice structure. Then, how do we solve the second problem? To solve the second species doubling problem of the Calabi-Fermion, there are 2 possible ways. The first possibility is that to identify species doubler which are in this momentum region is considered to be the super partner of some original state. This is a one-dimensional example. For example, phi is the original field, scalar field, and D is the auxiliary field. This is a super partner. Psi1 and Psi2 is introduced. So one can do these kind of things for a one-dimensional or two-dimensional as well. The second possibility is that for both fermion and boson, we introduce species doublers. Species doublers are automatically there. And we identify these species doubler states and original state for boson and fermions. This is a one-dimensional identification. In higher dimension, one one can do exactly similar way. For each direction, this P and 2 pi over A minus P is identified for the field. It's a bit strange because how come that the species diagram for the fermion has usually negative chirality? However, since we are just defining here the minus value, minus 2 pi over A minus P, therefore the derivative with respect to delta d delta dp for original point and species diagram point are the same, which is identified as the helicity physically. So therefore, because of this negative sign, identification for fermion is also possible. The coordinate representation of this relation can be identified in this way. Positive coordinate and negative coordinate is related with the alternating sign. So what this means is that this amount to consider only in the first quadrant of the coordinate space. We have introduced extra degrees of freedom by introducing half-lattice structure. So the degrees of freedom is doubled. But then, by this truncation, we only consider the first quadrant. But if you do like this, there is a corner here. Therefore, the lattice translational invariance is lost. However, Poincare invariance is okay for the actions, because if you use this derivative operator as a momentum operator. So in this way, we just try to solve the two problems at the same time. Let me give you the one example, which is a one-dimensional n equal 2 example of in the momentum space. Multiplication of the alternating sign to the field gives me in the momentum representation in this way, which is nothing but a species double state. Now the species Brillouin zone is doubled. 4 pi over A is the Brillouin zone now, because we introduced half-lattice structure. So this is one example. Species double state change, second supercharge field change into the species double state of the fermions. So that the original field and the species double fields comes into the game very naturally. And the exact Suji for this particular example, one-dimensional n equal 2, can be realized. I don't bother to write the action here. We have a beautiful exact Suji action, which is invariant under this transformation. This is a momentum representation of the dimensionless momentum operator, which is sine AP over 2. Previously, 2 over A was here. However, not everything is okay. We just took continued momentum to be this way. Since the absolute value of this one is smaller than 2 over A, there is a problem of the breakdown of the associativity. If we look at this product, phi 2, phi 3 product is taken first, and then comes the phi 1 product. Phi 1, phi 2 first, and then comes the phi 3 product. And then the relation for this product is this way, and that one is this way. Since each of the momentum is smaller, in this, if you look at this delta function, P2 hat plus P3 hat should be equal to Q hat. Therefore, Q hat is bounded in this way. Therefore, the summation should be bounded this way. For this product, for P1 hat plus P2 hat should be smaller to this one. Within this, if you look at the phase space, within this polygon is allowed region. But outside of these squares are the region where A and B are not overlapping, which means that associativity, these products are not equal to each other. So associativity is broken. But the question is, how do we recover it? If this limit is not there, if this is infinity, then maybe it's okay. So we try to find out we try to find out the delta P which satisfies the following relation. It could be minus infinity to plus infinity. The odd with respect to the lattice momentum reach to the lattice momentum in the continuum limit. And delta P should cover whole real axis twice with a period of 4 pi over a. And this truncation relation should be satisfied even for the momentum case. And at momentum plus minus pi over a should go to infinity. Then associativity condition is okay, at least from the phase space point of view. We found out a very beautiful solution, which is an inverse Gudamanian function. Since this function is a function of sine AP over 2, this relation is satisfied because sine AP over 2 itself satisfies this relation. And this function is a summation of the difference operator of all the lengths. It covers twice for the real axis. And it is symmetric with respect to pi over a. Pi over a, it goes to infinity, and minus pi over a, it just goes to minus infinity. So in this way, we have reached to the formulation, continuum equivalent lattice field theory formulation. And difference operator satisfies the exact Leibniz rule on the star product. No chiral fermion doublers because they are truncated. Associativity is satisfied for the star product. So, but this formulation is equivalent to the continuum theory. Let me just explain why I say so. Let's look at this relation. This is a convolution relation. Everything is now p hat. For the later use, I just write here the star product, but this is in fact the standard product. Here, delta pi over a is in plus infinity. Here is a plus infinity, and here is a minus infinity. So this is nothing but a convolution relation, except that the p hat itself is a function of the lattice momentum. Let's multiply dp hat, dp for both, and multiply 1 over f and 1 over f. This is 1. Here is 1. Here is 1 also. But changing the integration variable from p1 to p1 hat to p1, so that these things comes in. Then define phi tilde p as this function, where f can be anything at this moment. Then this expression can be written down in this way, where now the p are the lattice momentum. Now then, statement is, if we take delta p as the inverse Gudamanian function, and then take fp as derivative of the inverse Gudamanian with the square root, if we take this way, then the lattice to continuum and continuum to lattice has one-to-one correspondence. Namely, the lattice wave function can be converted into the continuum wave function through the transformation function, which has an explicit form. Let me write in this way. If we choose this way, then this guy comes in as a transformation function of J here. Well, delta G is a very complicated function of the inverse Gudamanian, but it's in the exponential. However, this function itself is very explicitly calculated. And actually, this is related to the Airy function, which Gerald Dunn stressed that the importance of this Airy function. So this is another example that Airy function comes in here in a very interesting way. But you can see that this is a non-local product. The question is, how much local or non-local for this function is? That's the question. Now, what I want to say is that lattice wave function when I defined in this way, these are the lattice wave function now. Phi delta cosine is now the lattice wave function because the momentum is from minus pi to pi. So this transformation function is defined from lattice to continuum and continuum to lattice, which I call J and J bar. They are very nice feature that just like plane wave function, argument is interchanged, is inverse. And eta is a continuum version of the lattice coordinate. And this J is, since it is a Airy function, so that it plays a role of the delta function. Looks like this. On the left-hand side, it is exponentially damped. On the right-hand side, it is an analytic continuation of the exponential, essentially. So that if you multiply this function to some other function, it plays a role of the delta function. So essentially, when I say this non-local product, these are the almost delta function. Therefore, this product is, even though it's non-local, it's almost local. So in this way, we found out the formulation of continuum theory and non-local lattice field theory is equivalently defined. But since it is continuum theory, so regularization is not yet done. So how do we regularize this kind of non-local lattice theory? Actually, we can just introduce the regularized version of the inverse Gudamanian function, where parameter z bar is introduced. If z bar is 1, then it's the inverse Gudamanian, which I used before. But if z is approached to 0, then it just comes to the symmetric difference operator, momentum representation of the symmetric difference operator. So this is the extrapolation regularization regulator. But if we introduce this type of the regulator, then inverse momentum representation of the inverse Gudamanian has an upper cutoff. So a given momentum, but what is interesting here is that for a given momentum, there are two parameters, A and Z hat. So for a given cutoff, lattice constant can be kept, while Z hat can be used as a regulator. So even for the lattice constant, finite, associativity has nothing to do with exactness of the supersymmetry as far as gauge symmetry is not introduced, so that the exact lattice Suji is realized. How do I understand this relation, which is continuum to the lattice? It's strange that continuum, countable infinity is corresponding to the continuum infinity in a way. Lattice is changed in lattice wave function, and continuum wave function has one-to-one correspondence through J. It can be identified as this Bloch spin-like transformation, except that in this case, Ginzburg-Wilson relation is exactly satisfied. But the regularized version has some needs some interpretation because regularization is now introduced. So what we are doing in the field theory application is that this type of momentum version of the Ginzburg-Bloch transformation is introduced. We can give a sort of the example of the Bess-Zumino, four-dimensional Bess-Zumino model, write down the momentum representation of the Bess-Zumino model, and replace the derivative into the Gudamanian, regularized Gudamanian derivative, and introduce interaction term, then the action keeps exact supersymmetry. Even though it has a regularized version. In 4-dimension, exact supersymmetry is kept. And since boson and fermion has a nice square relation for the propagator, vacuum energy can be exactly vanishing in the perturbative sense. However, there is a cutoff here. Unfortunately, we wanted to get rid of, to recover the associativity, but in order to regularize again, we have to introduce a cutoff there. Therefore, the associativity is again broken. But in order to prove the gauge invariance of this gauge invariant quantity, the gauge invariance of these things under the star product, associativity is needed. But it's broken now. Therefore, for the gauge theory, this is not perfect. However, in the limit, we know that it just, since it coincides with the continuum theory, therefore the associativity can be recovered as well. Then let me give you the conclusion. Continuum equivalent lattice field theory is defined. It defines non-local lattice field theory, but locality is recovered in the continuum limit. It is effectively local. Symmetry of the continuum theory are kept exactly. Especially Poincare symmetry is okay, supersymmetry okay, and no chiral fermion problems. Translational invariance of the lattice constant is lost, but Poincare invariance is okay if you use the derivative operator for the regularized version. N=1 reduction, which I didn't talk about so much, from N=2 to extended to N=2 to N=1 can be introduced because of the truncation. Degrees of freedom is truncated in a very natural way, so that extended to Suji to N=1 can be done. In the regularized version, associativity is broken. Therefore, the gauge invariance is recovered only in the continuum limit. There are some problems of the regulation, another kind of regularization. If we put this system in the box, then there are some problems for finding this solution. This formulation can be understood as a perfect action because for a given cutoff, there are two parameters, including lattice constant. Thank you.
Thanks. We have time for one or two very quick questions. Yeah, Georg.
So I just want to ask about this last red point there. So for the solution
yes.
of Nicolai and Dondi, there exist only trivial solution in a finite box with periodic boundary conditions. Is it for your solution different now, or this Gudemanian product, is it different?
The question is there a solution for this? That is your question?
Yeah, in this case.
No, if we use the Gudemanian and if you put the box regularization, then there is no solution for this one. That is the same as your analysis.
And so just another short one. I think if you have a doubling problem, you can easily also introduce Wilson term that is compatible with this star product. That should be possible, I think. But
you mean the introducing Wilson term? Yeah. Okay, we will discuss it later.
Any further questions?
Do you know how bad the violations of gauge invariance are as a function of this Z?
That's the next question which we have to ask. It's a very important question. And in order to overcome to the Spang-Mills, if this philosophy works well, then it will just go to the Spang-Mills as well. And then the question is, how bad it is a very good question. I think it can be understood from the Ginsburg-Wilson type analysis. But we have not yet done that.
regarding this statement about this Vesumino model, can you put superpotentials?
Yes, yes.
And can you show that they are not renormalized by perturbative?
Well, maybe these things should be analyzed numerically. And putting this formulation into the numerics is a big question. If somebody can do that, that's nice.
Just analytically, can you show in the lattice model that there is something protect, that there are some signatures of holomorphy and protection of superpotential?
You mean within this formulation, what can we say about that? That is the question. For a moment, I don't know. This is a good question.
Okay, so
I had a second question, which is, do you know the computational complexity for trying to evaluate this non-local product? Is it?
How difficult you mean?
Yeah. How many operations, if I want to evaluate the star product?
Yeah, if you truncate the product at a certain stage, then it is again the origin of the breaking. So, but it's, as this airy function has a very nice feature. So you don't need so much of the faraway step, I guess. This is probably, this should be understood somehow numerically. I don't know the detail.
okay, thank you.
Thank you.
Let's thank Professor Kawamoto again.